Okay, we started talking about kinetics, so we're going to talk about some of the rest of this and do a few more examples of stuff we did last time. But last time we got into kinetics, which is obviously really kind of a study of how fast or slow a reaction sort of proceeds. And we talked about a couple of things, specifically, we talked about what's sometimes referred to as the rate expression. And the rate expression really allows you to sort of relate everybody in the reaction in terms of how they're changing with time. So for example, here we could say that the rate is equal to minus 1/2 the change in the concentration of A over the change in time. Remember that when we do write the rate expression to take into account the stoichiometry that's in the equation, we take 1 over the coefficient, and that's sort of, again, as we talked about last time, does the stoichiometry part of the calculation along with the kinetics part of the calculation together. It is negative, as we also talked about, because it's a reactant. So over time, we should expect that the concentration should be decreasing with time. And that will equal negative the change in concentration of B over the change in time. Here, the coefficient is 1, which basically gives you 1/1, which is why people obviously don't put it in because it is just 1. We still have the negative here because it is still a reactant. When we get to the product side, we should expect it to start increasing with time. So we do have it as positive, and that'll be 1 over the coefficient there, change in concentration C over the change in time. The idea here is this is usually your average rate. That's usually a positive number. And because our reactants are decreasing with time, when you do final minus initial concentrations here, you will end up with a negative number. And that negative number and this negative that is in front will turn the average rate into a positive number, which is what it should be. You could kind of relate them all together. You could really just pull out, like we did in a couple of those examples, just the parts that you're interested in. And the relationship, again, if you're going to do something like that, is the rate is equal minus 1/2 change concentration of A over change in time. The rate is equal to, say, 1/3 change concentration of C over change in time. The idea here is just to say you know how A is changing with time. That would allow you to figure out the average rate for that reaction. The benefit of that is the same number that would be over here. And then that would allow you, for example, to figure out how C is changing with time. So that is how you could kind of relate these guys to each other. We also talked about that you could, if you wanted to, kind of do more of a stoichiometry problem first and then kind of do the kinetics part of it as well. It works the same way. The other sort of major thing that we talked about last time was the rate law, and the rate law has a general sort of form that looks something like this. And here, X, we have our rate for the reaction. That is our rate constant. And again, the rate constant is a constant value for a particular reaction at a specific temperature. X in this example and Y in this example are what are referred to as the orders with respect to A and B. You can again think about, as I talked about last time, sort of the orders are the proportion that you sort of need of each of those reactants to maintain a specific rate. One of the benefits of sort of knowing the rate law in a particular reaction is you can actually use that to your benefit if you, for example, find that you're working with a reaction that's maybe going too fast. You can play with the concentrations and you can slow it down if you needed to. You could also, if you have a reaction that's maybe going too slow, you could also play with concentrations and perhaps speed up the reaction. So the benefits of sort of knowing the rate law is very useful in a real life situation. Now, when we talk about the rate law, it is something that is found experimentally. So this is always sort of found experimentally. And the orders are not the coefficients from the balanced equation. And that usually means that usually in these problems, you have a table where you have a number of experiments listed. You usually will have the concentration of your reactants listed, and you will usually have an initial rate listed for each of those sort of experiments. And probably the best way to sort of figure out the orders is, as we talked about, you could do this sort of mathematical approach where you take rate 2 over rate 1. And the idea when you're sort of choosing this is you want to come to the table and you want to find two entries in that table, two different experiments, where one of the concentrations stays the same. So, for example, if A stays the same and B varies. And what that will give you is basically one unknown. You would put into here, for example, if I chose 1 and 3 in my example, and 3, by the way, if it had like the larger rate, I would put that probably up on top again. It'll give you the nicer whole numbers. You can do it the other way, just get more of a decimal sort of form. But if you do this, you put everything from, say, experiment 3 up on top, everything from experiment 1 on the bottom, and it will kind of cancel out again. You'll get something maybe like 4. And then at this point, we don't know what that is, but it is a constant, so it should remain the same. And since the x's here should also be the same, and the concentration of A is constant, those guys would cancel out and maybe get like a 2 to the y, where y would equal 2. Again, you can take the natural log of both sides if you don't have a nice pretty number that's happening, and then divide it to the other side, and you'll end up with the same answer. So that is, again, mathematically how you solve it. The idea is you would use the table of information to figure out the orders. Once you have the orders, you then can have the completed rate law, and then you could go back in and solve for something like what the value of the rate constant is by putting in the values from the table. And when you go to the point where you're solving for the rate constant, it doesn't matter really which entry you choose. They all should give you basically the same rate constant because it should be a constant value. Any questions on any of that there? All right, so we did a couple examples. Why don't we do a couple more here just to make sure? So let's try this one here. What is the rate law? What are the orders, the overall order, and what is the value of K? Okay, so let's take a look. So once again, in this case, we could write sort of the generic rate law here before we figure out the orders. The rate is equal to K times concentration, in this case, of NO2. We'll make that an X, and CO, we'll make it a Y. Remember as well, kind of a difference between the rate law and the rate expression. The rate law only deals with reactants, so no products in the rate law. So remember, when we're doing this, we're looking for two entries where one of the concentrations stay constant and one varies. So just looking at it here, 1 and 2 will achieve that for us. That's going to keep the CO constant and vary the NO2. So if we look at experiments 1 and 2, again, we're going to take the larger rate on top. You don't, again, have to do that, but it gets you a little bit nicer number sometimes. So I'm going to put number 2 up on top. And what I'm going to do is basically just put all the information for experiment 2 up on top. And in this case, my concentration would be 0.2 to the X. And my other concentration there would be 0.1 to the Y. We're then going to put everything for experiment 1 there on the bottom. And again, here we got 0.1 to the X and 0.1 to the Y. Once again, we're just going to divide everything out here. So 0.0082 divided by 0.00821. Going to give us basically a 3.9, which is pretty close to 4 in this case. That will get rid of the K's because they are constants. When we divide that, that will give us a 2 to the X. And once again, although we don't know what Y is, it is the same on top and bottom, which means that should completely cancel out. Again, in this case, I'm going to round it. It's close to 4. And that means that in this case, X would equal 2. Any questions on that there? Again, you could take the natural log of both sides and divide it. So if you were to do that, you could take the natural log of 3.9, it equals, divided by the natural log of 2, it equals, and you'll get basically like a 1.96, which again is fairly close to 2 if you kind of do that. And sometimes they may not be perfect numbers. You can do a little bit of rounding because they are based on experimental information. So same thing with the experiment you did yesterday. Again, you could probably round to the closest whole number when you do solve for the orders. Now that we kept CO constant, we then want to go back and keep the NO2 constant. It looks like in this case, we can go with 2 and 3. And by the way, we could also have done on the first one, 1 and 4, or 2 and 4 as well. It should come out basically the same. So we're going to look at experiments 2 and 3. And here we're going to go with, I guess 3 is slightly larger, 0.0083 molar seconds up on top are 0.2 to the X, 0.2 to the Y. Putting number 2 on the bottom there, 0.0082, K, 0.2, and 0.1 here to the Y. When we do this, basically get 1. Again, their K's will cancel. These guys are going to completely cancel. And when we do that, it's going to give us a 2 to the Y. A reminder, right, that if you take something to the 0 power, right, that is what's going to equal it. 1. And again, if you take the natural log of 1, you will get 0. And divided by natural log of 2 will give you 0 as well. So that is the orders for this reaction. That means that our really completed rate law is the rate is equal to K times NO2 squared. Now, because the CO is 0 order, you could do one of two things. You could leave it off in terms of the rate law like I did here and not even have it in there. If you are to put it in, you do need to make sure that I'll just go underneath here. You write it like this, and you do put a 0 on top of it. Because if you do not put the 0 on top of it and just put it in with nothing written there, it is implied that it is first order, right? So you got to make sure if you do want to include it, you got to put the 0 in this particular case. Again, if you don't put that 0 and you leave it in there, people think it's first order. So probably could just leave it out since obviously it's not going to be the one that's affecting the rate at all. The overall order in this case would then be 2 plus 0, which is second order overall by just adding those guys together. Now that we do have the completed rate law, we could solve for the rate constant. K would equal the rate divided by NO2. And again, we do need to square it. At this point, we could absolutely choose any one of these entries in this table to solve for it. So I'm just going to take the first entry, and that would give me 0.0021 molar seconds divided by our NO2, which is 0.1 molar squared. And that will get us here. What's in there? Looks like 0.21. In terms of the units, molarity on top, and really one of the molarities on the bottom will cancel, gives us 1 over molar seconds as our units. By the way, again, as we talked about yesterday, that is 2 letters, which matches the second order type of thing. Any questions on how to do that there? All right, so that's just one more example like we did yesterday, and obviously it's very similar calculation to what you need to do for the lab that we did yesterday as well, and obviously you're responsible for that for the final. All right, let's take a look then at some other stuff here.